When I was thinking about how to present computers in this series, one question kept coming up. How do you explain the role of mathematics in the development of computers when most people think that they're really only one subject? Well, one way to tell this story would be to look at computers as tools for doing quantitative things, like solving large problems with lots of computation. And then we could tell the engineering part of the story, how we went from large and rather simple computers to small and pretty complex ones. But that's only part of the story, and the relationship between mathematics and computer science is extremely subtle. So maybe the best way to tell the story is to start at the beginning. And at the beginning is a question that we really haven't even asked in this series, namely, what is mathematics? Oh, I know, we've done a lot of mathematics here, and we've shown a lot of important contemporary applications, but we really haven't looked at the foundation of the subject. What makes mathematics mathematics? Well, at the heart is the relationship between proof and truth. Now, proof is just manipulation of symbols through some fixed rules, the scratches on a piece of paper. But truth has to relate somehow to the real world that mathematics is trying to discover things about. So the relationship of math to the world, of proof to truth, has to be our starting point for investigating what is mathematics. The study of the relationship between truth and proof really became focused in 1900 when David Hilbert set forth his famous program. He literally set a research agenda for hundreds of mathematicians. You might wonder how one man could do that, but you have to understand what European science was like at the time. It really operated on the great man theory, where individuals wielded enormous power, and Hilbert was the great man of mathematics. Now, in terms of proof and truth, the Hilbert program had two goals. He wanted to show that mathematics was consistent and complete. Now, by consistent, all it's meant is that you can't prove something, then turn around and prove its exact opposite. And by complete, you mean that everything which is true can be proved. Now, those sound like some pretty simple questions. Why weren't they asked and answered thousands of years ago? Why 1900? Well, the groundwork hadn't been laid. And around the turn of the century, many threads were coming together. First of all, you had the shock of non-Euclidean geometry, which really made mathematicians realize that they had to separate mathematics, these scribbles on a piece of paper, from the world that math was trying to describe. Because, mathematicians were coming up with worlds that were totally outside of common experience. Now, at the same time, you've got logicians like Boole and Russell and Whitehead who were developing the language of symbolic logic, which enabled us to formalize the study of proof within mathematics. And then there were some very disturbing self-referential paradoxes. What do I mean by self-referential paradox? Well, let me give you my favorite example. Imagine a small town which only has one barber, and we'll say that the barber shaves everyone who doesn't shave themselves. Question: does the barber shave himself? Well, think about it. If he shaves himself, then since he only shaves people who don't shave themselves, then he doesn't shave himself. And if he doesn't shave himself, then since he shaves everyone who doesn't shave himself, then he does. Well, that may just sound like something cute, but what was amazing was that these same kind of paradoxes were coming up within mathematics. Let me give you an illustration. Consider the mathematical idea of a set. Now, a set is just a collection of objects, and generally speaking, sets don't contain themselves. For example, the set of all houses is not a house, but sometimes they do. The set of all concepts, for example, is a concept. So consider the set of all sets which are not elements of themselves. Question: is that set an element of itself? Well, if it is, then it isn't. And if it isn't, then it is. The Barber paradox. So the hope of the Hilbert program was to put these paradoxes to rest. To prove that mathematics was consistent and complete, as Hilbert and everyone else firmly believed. His plan was to settle these questions once and for all, and construct a firm foundation for all future work in mathematics. For the next 30 years, mathematicians were hard at work on the Hilbert program. Now, what does it mean to be hard at work in mathematical logic? Well, it means total concentration, living inside an abstract world until that world becomes real to you. Let me tell you a story to illustrate what I mean. One researcher at the time was a young Austrian mathematician, Kurt Gödel. Now, Gödel came to this country and got a job at the Institute for Advanced Study in Princeton. He wanted to become a U.S. citizen. Well, Gödel didn't just go out and memorize the names of the Secretary of State and the Secretary of Agriculture. He got the Constitution, he got every book on the subject he could get his hands on. Well, the story goes that Gödel was able to find a perfectly constitutional way in which the United States could become a dictatorship. Well, Einstein drove Gödel to his swearing-in ceremony, and before the ceremony, Einstein and Gödel and the judge were talking, and Gödel was telling the judge some of the things that were going on in Europe and in Germany during those days, which was the early 30s. And the judge was appalled, and he looked at Gödel and he said, well, thank God nothing like that could happen in this country. And Gödel looked at him and he said, well, you know, Your Honor, actually it could. All you have to do is... Einstein had to drag him away. Well, with a mind like that, maybe it's not so surprising that Gödel was able to set the mathematical world on his head. Because what Gödel showed was that if a mathematical theory was powerful enough to do simple arithmetic, then in fact, if that theory was consistent, we couldn't prove its consistency, and that there were true statements which we could never prove. Now, the proof of Gödel's theorem is pretty complicated, but it rests on a rather simple idea. Gödel noticed that if you looked at all of the mathematical symbols and all of the mathematical statements and all of the mathematical proofs, then you could list them. I mean, you could number them. And with a clever coding scheme, he was able to find a statement which said, the statement with Gödel number 178, say, cannot be proven. And sure enough, that statement had number 178. In other words, Gödel was able to get a statement which said, I am unprovable. It's just a form of the famous liar paradox. You know, I am a liar, and if you're lying, you're telling the truth. If you're telling the truth, you're lying. So, in other words, Gödel found a true statement which was unprovable. The Hilbert program was gone. It's impossible to overestimate the profound effect that this result had on mathematics and on mathematicians. I mean, mathematics was always this clean, straightforward subject, but now it turned into something else. And this was really upsetting. I mean, some people actually left the field. Other people, myself included, find this really exciting because it means that mathematics shares a common bond with all human endeavors: uncertainty. But how much uncertainty is there? I mean, one natural new question to ask would be, well, could we decide which were these unprovable statements? Then we could just sort of put them aside and work on the ones that at least we have some chance of getting somewhere with. Well, the British logician Alan Turing looked at this question, and he phrased it in this way. He said, can we find a procedure for determining which of the statements of mathematics are unprovable? Now, even in order to work on that problem, Turing had to come up with some formal notion of what was meant by a procedure. And in order to do this, he came up with the idea of a machine. I mean, just a mental construct for what soon became known as a Turing machine. Now, this machine of Turing's had inputs, it had a tape with symbols, and it had outputs. And you could carry out regular procedures like addition and multiplication. And then Turing said that you have a procedure if you can build a Turing machine to carry it out. Well, using this definition, he was able to show that, in fact, there was no procedure for determining whether a mathematical statement was provable or unprovable. In other words, not that just that it was hard, but of all possible Turing machines and all possible sets of rules, there was none that could figure out this problem. So the situation is about as bad as it could be. Gödel shows that there are unprovable statements, and Turing comes around and says, you can't decide in advance which ones they are. But if you look at the story, there's some good news, because even though Turing's idea was just that, just an idea of a machine, if you look at what went into it, I mean, he had inputs, he had a tape, he had symbols, he had outputs. You have elements that we all recognize as going into a modern computer. We've been looking at the development of fundamental mathematical ideas from Hilbert's program to Turing's machine. There was still a long way to go to turn the notion of a Turing machine into a practical working computer. That story involves many characters, but I'd like to talk about just one, John von Neumann, one of the finest mathematicians of this century. Von Neumann's early work was in logic. In fact, he worked with David Hilbert in the 20s on the foundations of mathematics. But in the same period, he produced an important paper on the mathematical basis of quantum physics. This combination was typical of von Neumann. He was a pure mathematician who was also fascinated by practical applications. It was partly his interest in solving difficult physics problems that led von Neumann to computers. But what's so fascinating about von Neumann's involvement with computers is that there are so many ways to understand it. His interests ranged from numerical analysis to neurophysiology, and in almost every case, he could see connections with the automatic computer. Above all, we have to keep in mind that he was trained as a logician and was well aware of the links between logic, proof, and computation recently established by Gödel and Turing. So von Neumann began to work on computers. His mathematical approach led him to a major insight. He could describe the logical structure of a computer without worrying about the technological details of how it should be built. As he did in so many other fields, but perhaps nowhere with consequences of such magnitude, he brought mathematical thinking to bear on the design of computers. And not just theoretical design. He actually directed the construction of a computer embodying his ideas. The machine was built in the late 40s at Princeton and became the prototype of the modern computer. Of all von Neumann's ideas about computers, one stands out as a monumental achievement: the stored program. Perhaps only a logician could have invented the stored program. This was, after all, the age of Gödel, whose profound insight was that a mathematical statement could be represented or coded by a number. Von Neumann saw that the same could be done for a computer instruction. Instructions could be coded as numbers and stored in memory like data. The consequences of this idea were enormous. It made programming, for the first time, a practical proposition.
The older machines required one to clumsily perform hand pluggings of connections, which took hours, indeed days. It meant that programming was an art, in fact, a very black art. And furthermore, it meant that the total number of instructions one could write were comparatively small.
Great as the stored program concept was, it wasn't von Neumann's only contribution to computing. He also made computing fashionable. In the history of science and technology, after all, it's not just the quality of ideas that matters. Connections and influence can be just as significant.
His great prestige as a mathematician sold the notion of the computer and its great importance to the industrialists and to the government officials who made this whole development possible.
Scientists were also quick to see the importance of the computer, finding uses for it as a research tool in all kinds of fields. Ironically, mathematicians have been holdouts for the most part, but this is changing, and the computer has started to play a role in the creation of new mathematical results. One way this can happen is by using the computer to explore ideas. Computer graphics, for example, helped two mathematicians analyze surprising new members of a special class of surfaces called minimal surfaces. Now, just what is a minimal surface? Here's a simple example. How many surfaces have this hoop as a boundary? Well, they're an infinite number. Just think of all the different mountain peaks that you could have with this circular base. So, of all the surfaces that have this boundary, which has the minimum area? We can find the solution with a solution. When I dip this hoop into the solution, the soap forms a film. This film is stable only when tension is distributed equally over the surface, and that happens when surface area is minimized. So physics provides us with the minimal surface, in this case, a flat disk. Now, the disk can also be proven mathematically to be the surface of least area. If I use two hoops and separate them, I get a surface that forms this hourglass shape called a catenoid. Now, the catenoid has the least area of any surface attached to both hoops. The two minimal surfaces we've seen so far, the disk and the catenoid, have an important property. They don't intersect themselves, so they could be the boundaries of real objects. We'll call surfaces like this natural. Surfaces that intersect themselves, like this one, don't occur very frequently in nature. But until recently, mathematicians had found only 3 examples of a certain kind of natural minimal surface. Aside from the catenoid, there's the plane and the helicoid, a sort of infinite screw. The helicoid was the last of these to be discovered, and that was back in 1776. So mathematicians were pretty surprised when, after a hiatus of over 200 years, a series of new examples was discovered.
This is a picture of the surface that Bill Meeks and I proved was a surface that was free of self-intersection or natural. It's a minimal surface, and it was found first by Celso Costa, a Brazilian mathematician, in about 1981. But it was found in terms of very complicated equations, and from the equations it was virtually impossible to tell what properties it had. Our idea was to simulate the surface on a computer by solving the equations numerically. And after several sleepless nights and at the time rather crude graphics, we could see, in fact, it was the example we were looking for. It was free of self-intersection. It was the one that people had been trying to find. The most important and the most surprising thing we saw in the early computer pictures of the surface was that the surface was highly symmetric. Let me explain the symmetries of the surface by looking at this baseball. The symmetries of the surface were identical with the symmetries of the seam of the baseball. If you cut the baseball in half like this, you get 2 pieces, one of which is a mirror image of the other. You could also slice in half like this, and you get 2 pieces, one of which is a mirror image of the other. Finally, there are 2 rotations on the surface that take the seam into itself. Here's one, and here's the other, around this line. Once we observed this surprising symmetry on the screen, we were actually able to take this information back to the equations and greatly simplify the problem. And it was in this way that we actually created a mathematical proof that this surface was free of self-intersections. While we were doing it, we actually used the computer to test out various hypotheses. So it's fair to say that the computer acted not only as an inspiration in this process, but as a guide in the creation of the proof. After we had analyzed the first example, a model of which I have here, we soon began to believe that this was not an isolated example, and we started trying to use this one as a clue to how to construct new minimal surfaces without self-intersection. The first thing we thought of doing was to increase the number of tunnels, and in fact that was possible. Here's the next more complicated one, and in fact it's possible to make an infinite number of examples. A second way to make new examples would be to cut off the bottom of this one and add a reflected copy of itself. In fact, we can stack an arbitrary number one on top of the other. A third way would be to take this example and smoothly distort it, making the bottom somewhat fatter and the top progressively thinner. If you look from the 18th century to the 19th century and then to the 20th century, what was considered good mathematics, pure mathematics in vogue has changed, and I think it will change. It will change because of the availability of high-speed computation and the natural power that brings to certain problems and the questions that the computational process itself poses for theoretical mathematicians.
We've just seen how a computer helped mathematicians make an important discovery. To find minimal surfaces, Hoffman and Meeks used the computer as an experimental tool, a convenient way to develop their ideas. But I started this show by talking about proof, and now we'll look at the essential role computers played in the proof of an important theorem. The problem has to do with map making. To make distinct borders, neighboring countries must have different colors. So how many colors do we need? It's easy to see that 3 colors aren't enough, so we need at least 4. The question becomes, is 4 enough? Mathematicians suspected as much for years, but it's one thing to conjecture and quite another to prove. Remember, Gödel showed that mathematics contains unprovable truths, And after a conjecture has gone unproven for 100 years, mathematicians begin to wonder. But in 1976, two mathematicians at the University of Illinois, Kenneth Appel and Wolfgang Haken, found a proof. Their methods were remarkable. It was the first time in the history of mathematics that an important proof relied on computers to verify details that no single person could ever check. Now, as it happens, one mathematician did make substantial progress on the conjecture 100 years ago. Alfred Kemp, an English barrister, made the problem more manageable by defining a special kind of map called a normal map. Not all familiar maps are normal in this sense. The map of the United States is not normal because Utah, Arizona, Colorado, and New Mexico meet at a point called Four Corners. And this map of Africa isn't normal because South Africa surrounds Lesotho. Kemp showed that if all normal maps could be colored with four colors, then so could all maps. That cut down the scope of the problem and made possible an even bigger cut. Kemp could then prove that any normal map must have a country with less than 6 neighbors. This isn't at all obvious, but if you try to draw a map in which every country has 6 or more neighbors, you'll find it's impossible. Kemp's result, then, is that a map cannot avoid having a country with either 2, 3, 4, or 5 neighbors. A final attack was now possible. You could take these 4 cases and try to prove one by one that they cannot occur in a map that needs 5 colors. And that's just what Kemp set out to do. Let's look at the proof of the 3-neighbor case. First, assume for the sake of argument, as Kemp did, that there are maps that need 5 colors. Then we can pick the map that has the fewest countries. This map is called the minimal 5-color map. Notice that the country in the middle has 3 neighbors. Let's combine it with this other country to make a new map. Since this new map has 1 less country, we can color it with 4 colors. That's because the map we started with was the smallest map that needed 5 colors. Now let's restore the country that was next. Its neighbors use up 3 colors, so we can give it the 4th color without causing problems. But this is a contradiction. This map was supposed to need 5 colors, and we've gotten away with 4. What does this mean? There is no such thing as a minimal 5-color map that has a country with exactly 3 neighbors. You can now see the complete strategy for the proof of the 4-color theorem. It's based on 2 key ideas. One is unavoidability, identifying the small number of situations that you have to deal with. The other key idea is reducibility. We just saw that if a 5-color map has a country with 3 neighbors, we can reduce the number of colors from 5 to 4. So a reducibility proof shows that a particular kind of map never needs 5 colors. The strategy is now to show that all of the other unavoidable situations are also reducible. Well, Kemp found similar proofs for the cases of countries with 2 and 4 neighbors. At this point, there's only one case left. And Kemp thought he had a proof of this 5-neighbor case. But 11 years after he published it, an error was found. And despite an extraordinary amount of work on the problem, the 5-neighbor case remained unsolved for the next 100 years. Then, starting in the early 1970s, Appel and Haken found a way to treat the 5-neighbor case as a number of subcases. They proved that if a map has a country with 5 neighbors, then it must contain one of these 1,500 partial maps somewhere within it. All these subcases make up a new unavoidable set. So Kemp was on the right track. There were just many more cases to consider than he guessed. Appel and Haken still faced the hardest part of the problem, proving reducibility. For each case, they had to show a contradiction. If that case was part of a 5-color map, then you could actually color that map with just 4 colors. Now, to prove reducibility for all 1,500 cases, Appel and Haken had to look at about 10 billion different colorings. No one mathematician could check each coloring by hand. Life is just too short, literally. And that's where the computer comes in. Checking all the different colorings is a long and repetitive job, ideally suited to computers. about 1,200 hours of computer time were needed to show that all of the unavoidable cases were in fact reducible. The four-color theorem was proved. Now, this is a strange kind of proof. The computer wasn't a mere convenience. The results of its programs are an indispensable part of the proof. And because of this, some mathematicians have been troubled. I mean, I always thought of a proof as something that I could check. So should the four-color result be considered a proof even though no one human mathematician can verify it? Well, in a sense, we've come full circle. We've looked at the effort to remove ambiguity and paradox by formalizing the notion of proof and its relation to truth. Computers were born in part out of that effort. But 75 years after Hilbert, when a computer plays an essential part in proving a 100-year-old conjecture, new questions come up. Now, I think that this is the best news of all, because unlike popular misconceptions, mathematics is alive and vibrant. It's reviewing its meaning and its purpose, constantly expanding and renewing itself.